Welcome to quantum error correction, one of the most fascinating and important challenges in modern science and engineering. At its heart, this topic is about fundamental problem. Quantum computers are incredibly powerful in theory, but in practice, they make mistakes constantly at this very moment. And those mistakes are unlike anything we deal with in classical computing. To unlock the true potential of quantum machines, we need to understand why error happen and how to fight them. This module will take you on a journey from the basic physics of why quantum systems are so fragile all the way to the sophisticated mathematical tools that engineers and physicists have invented to protect quantum information. You will encounter some of the most elegant ideas in all of computer science, ideas that show how nature's own rules, which seem to make the problem impossible, can actually be turned into a solution itself. By the end of this module, you will understand the key error correction codes that researchers use today, how fault tolerant quantum computers are designed, and why there is a critical boundary called the threshold that separates quantum computing works from quantum computing fails. This is the enduring frontier of our generation. This is your Professor Atif Reed Muhammad, Lecture 9, and it's at Marshall University. This module is organized into four major sections that build on each other in a logical sequence. We begin by asking the fundamental question: why is this problem so hard in the first place? Understanding the nature of the challenge is essential before we can appreciate the elegance of the solutions. Just as a doctor must understand a disease before prescribing medicine, we must understand quantum errors before we can correct them. From there, we move into the theoretical barriers, the laws of physics themselves that seem to make quantum error correction impossible. This barrier or these barriers are not engineering problems that better hardware can solve. They are deep mathematical facts about the universe. Learning how scientists cleverly worked around them is one of the most intellectually satisfying stories in modern physics. Third and fourth sections cover the actual tools, the specific codes that engineers use to protect quantum information, and the broader framework of fault-tolerant computation that ensures the entire computing process, not just the data storage, remains reliable. Each section connects directly to current real-world hardware efforts, so this is not just abstract theory, but the blueprint for machines being built right now. So why quantum error corrections matters? Imagine building a world's most powerful calculator. But every time you press a button, there is a small chance the calculator quietly changes one of the numbers you already entered. If your calculation only has a few steps, this might not matter much. But if your calculation has millions of steps, which is exactly what a useful quantum algorithm requires, those small random changes accumulate until your final answer is completely meaningless. This is the predicament that quantum computers face every single moment they are running. The gap between where quantum hardware is today and where it needs to be is genuinely staggering. Current quantum processors make errors at a rate that would be completely unacceptable for any real computation. The error rate needs to drop by a factor of roughly 10 billion, not 10, not 1,000, not 10, but 10 billion, before a quantum computer could reliably run the kinds of algorithms that might or would make it useful for solving real-world problems like drug discovery or cryptography. Quantum error correction is the field that bridges this gap. It does not try to make individual qubits perfect. That may never be physically possible. Instead, it accepts that individual qubits will make mistakes and builds a system where those mistakes can be detected and undone before they poison the final answer. It is, in essence, the field that turns a fragile curiosity into a reliable tool. The promise of quantum computing. Before diving into the technical challenges, it is worth pausing to appreciate what is at stake and why so many brilliant scientists are working on this problem. Quantum computers are not simply faster versions of the computers we use today. They operate on fundamentally different physical principles and are capable of solving certain categories of problems that would take classical computers longer than the age of universe to crack. The potential applications touch virtually every domain of human knowledge. In medicine, quantum computers could simulate the behavior of molecules at the atomic level, permitting researchers to design new drugs with a precision that is simply impossible with today's tools. In materials science, they could help discover new superconductors, better batteries, and stronger lightweight materials. In finance and logistics, they could solve incredibly complex optimization problems, finding the most efficient routes, the best investment strategies, or the optimal distribution of resources across global supply chain. All of these transformative possibilities share a single prerequisite. The quantum computer must produce reliable, accurate results. A quantum computer that makes uncorrected errors cannot solve any of these problems, no matter how many qubits it has. Quantum error correction is therefore not just a technical detail, it is a key that either unlocks or permanently locks the door to the quantum computing revolution. Decoherence and quantum noise. We have been discussing decoherence a while back, as well as we have also explored the idea of quantum noise. To understand why quantum computers make mistakes, you need to appreciate just how delicate quantum states are. A qubit does not just hold a 0 or 1, it can hold a kind of blend of both at the same time, and the way those possibilities are balanced and related to each other is itself part of the stored information. This blended state is extraordinarily sensitive to the surrounding environment. Any stray vibration, electromagnetic fluctuations, or random thermal energy can quietly nudge the qubit and distort the delicate balance. We have discussed this in quite depth. This process of quantum state being disturbed by its environment is called decoherence, as we already discussed and learned about it. There are several distinct ways that errors can enter a quantum system, and engineers have given names to each type. Some errors cause a qubit to spontaneously flip from one of the value to the other over time, like a coin that randomly flips itself. Others scramble the phase relationship between the blended components of a qubit state without changing the apparent value. A subtler and in some ways more dangerous form of corruption. There are also errors introduced during the operations themselves, when the precise pulses of microwave or laser energy used to manipulate qubits are not perfectly calibrated. Perhaps most troubling is that nearby qubits can accidentally influence each other in ways that were not intended. This crosstalk means that an error on one qubit can spread like contagion to its neighbors. There is even a failure mode where a qubit leaks out of the two-state system. It is supposed to inhibit this and starts behaving like more complex quantum object, breaking all the assumptions the error correction system was built on. Each of this error type requires a different kind of vigilance from the quantum engineer. So T1 relaxation, energy decay, qubit spontaneously drop. T2 dephasing, phase noise, superposition phase randomizes without energy change, destroying coherence. Gate errors, imperfect pulses introduce systematic and random errors during qubit operations. Measurement errors Readout circuits misidentify qubit state during syndrome extraction crosstalk. Unintended interactions between neighboring qubits corrupt multi-qubit gates. Leakage. Qubit escapes two-level subspace into higher energy levels of physical system. And we have looked at qubits are quantum mechanical systems. Any uncontrolled interaction with the environment destroys the delicate quantum information encoded in superposition and entanglement. The no cloning theorem. Here is where the story gets philosophically interesting. Your first instinct of protecting information against errors might be just make backup copies. If your hard drive fails, you restore from backup. If one copy of a document gets corrupted, you still have the other. Classical computers do exactly this. They use redundancy as their primary defense against error. Quantum mechanics, however, has a law that specifically forbids this strategy for quantum information. This law is called no cloning theorem. The no cloning theorem, proven in the early 1980s, states that it's physically impossible to make a perfect independent copy of an unknown quantum state. This is not a limitation of current technology that engineers might someday overcome. It is a fundamental consequence of how quantum mechanics works at a mathematical level. If you try to copy a quantum state, the very act of interacting with it to copy it disturbs it, destroying the original in the process. You cannot read out the full information in a quantum state, write it elsewhere without erasing it. This theorem seems to make quantum error correction completely impossible. Yet, here we are studying a whole field dedicated to doing exactly that. The brilliant insight that made quantum error correction possible is that you do not need to copy the quantum information, you need to spread it. By entangling a single logical qubit across many physical qubits in a clever pattern, you distribute the information so that no single qubit actually holds enough of it to be readable. But the pattern as a whole preserves it perfectly, and crucially, you can check for errors by measuring the relationships between qubits rather than measuring the qubits themselves. Classical versus quantum error correction. To appreciate how different quantum error correction is from the classical counterpart, it helps to compare them directly. In classical computing, errors are simple. A bit is either 0 or a 1, and an error is just a bit getting flipped from one to the another. Detecting this is straightforward. Make 3 copies of every bit, and if one disagrees with the other 2, it is the one that is got flipped. This majority vote approach has been used in everything from spacecraft computers to everyday hard drives for decades. Quantum error correction faces a completely different landscape. First, the errors themselves are far more varied. Instead of just bit flips, quantum errors can be arbitrary rotation of a quantum state in a continuous space of possibilities. Second, you cannot simply make copies of the quantum state to compare against each other, as we just discussed. Third, and perhaps most subtly, the very act of measuring a qubit to check whether it has an error destroys the quantum information you are trying to protect. In classical computing, reading data does not change it. In quantum computing, measuring data collapses it. The solution quantum physicists developed involves a clever workaround for each of these problems. Error through continuous in principle can be forced to snap to a small discrete set of possibilities when you probe the system in a right way. Redundancy is achieved through entanglement rather than copying. And error checking is done by measuring relationships between qubits, asking questions like, are these 2 qubits the same as each other, rather than what value does the qubit have, which reveals errors without collapsing the stored information. The continuous nature of quantum errors. One of the most intimidating aspects of quantum error correction is when you first encounter it is the idea that quantum errors are continuous. In a classical world, errors are all or nothing events. Either a bit flipped or it did not, but a quantum bit can be rotated by any tiny moments in any direction in a highly dimensional space of possibilities. At first glance, this seems to make the problem infinitely harder. How can you correct an error when it could be any of infinity, many different things? The answer to this puzzle is one of the most elegant ideas in all of quantum information science, and it is what makes quantum error correction theoretically possible at all. It turns out that any quantum error, no matter how arbitrary and continuous it might be, can be mathematically decomposed into a combination of just four basic types of operation: doing nothing, flipping the qubits, flipping its phase, or doing both simultaneously. These four operations are called the Pauli operator, named after the physicist Wolfgang Pauli. They form a complete set like primary colors that can mix the produce as any shade, and that can mix to produce any shade. When you probe a quantum system with the right kind of measurement, nature effectively forces the continuous error to pick one of these discrete categories. The error collapses from an arbitrary rotation into one of just a handful of well-defined error types. Once you know which discrete type of error occurred and where it happened, you know exactly what correction to apply. This discretization of errors is mathematical miracle that makes quantum error correction not just possible in principle, but practically implementable with real hardware. Quantum error correction, the core principles. The process of quantum error correction follows a clear sequence of steps, and understanding this pipeline is essential for everything that follows. The first step is encoding. You take the fragile quantum information you want to protect, your logical qubit, and spread it across multiple physical qubits using a carefully designed pattern of entanglement. The information is no longer localized in any one place. It is distributed across the whole group in a way that is invisible to any individual qubit but encoded in their collective relationships. Once encoded, errors will inevitably occur. Some qubits will get flipped, others will have their phases scrambled by the environment. The next step is syndrome measurement, and this is where the cleverness really shows. Special helper qubits called ancilla qubits are brought into contact with the data qubits in a way that lets them absorb information about what errors have occurred without absorbing any information about what the actual data says. When you measure these ancilla qubits, you get a pattern of results called error syndrome. This syndrome is like a fingerprint that identifies the type of location of the error. The final two steps are decoding and recovery. A classical computer reads the syndrome pattern and figures out the most likely error that could have produced it. This is the decoding step. Then a correction operation is applied to the physical qubits to undo the identified error, restoring the logical qubit to its original state. The beauty of this pipeline is that at no point did anyone directly measure or observe the actual quantum information being protected. The error was found and fixed entirely through indirect evidence. Most practical quantum error correction encodes in specifically coding are described using a mathematical framework called stabilizer formalism. While the name sounds intimidating, the underlying idea is quite intuitive. Think of the correctly encoded quantum state as a very specific pattern of relationships between qubits. The stabilizer generators are essentially a list of questions you can ask about those relationships. Questions whose answers should always be yes. If no error has occurred, when an error happens, it breaks one or more of those relationships, and questions start returning no instead. The power of this framework is that the questions are designed so that their answers reveal which error occurred without revealing anything about the actual data. You can think of it like checking whether a jigsaw puzzle is assembled correctly by asking whether adjacent pieces fit together properly. You can tell if a piece is in wrong place without needing to read what the picture on the puzzle shows. Each generator is like checking on set of adjacent pieces. The collection of all the yes or no answers you get forms the error syndrome. A key parameter in this framework is the distance of the code. A measure of how many errors would need to occur simultaneously to fool the system into thinking no error happened. A code with a higher distance can correct more errors, but generally requires more physical qubits to encode each logical qubit. Designing codes that achieve high distance with as few physical qubits as possible is one of the central engineering challenge of the field, and it is the problem that motivates the search for better and the better code families. The Shor code, proposed by mathematician and computer scientist Peter Shor in 1995, holds a special place in the history of quantum computing because it was the first proof that quantum error correction was genuinely possible. Before Shor, many physicists believed that decoherence would be an insurmountable barrier to practical quantum computation. Shor's code demolished that pessimism by providing an explicit, concrete construction that could correct any possible error on a single qubit. What makes the Shor code particularly important historically is not just that it works, but what it corrects. Unlike earlier attempts that could handle only qubit errors or only phase flipping errors, the Shor code handles both simultaneously. Bit flip errors are the quantum analog of a classical bit flip. The qubit's value gets inverted. Phase flip errors are more subtle and have no classical analog. They scramble the relationship between the two components of a quantum superposition without changing which value you would see if you measured it. The Shor code was the first to show that a single encoding could defend against the both attack vectors at once. The code uses 9 physical qubits to protect a single logical qubit, which was quite an expensive trade in terms of resource overhead. Later codes would improve on this efficiency significantly, but that inefficiency is forgiven when you consider what a Shor code achieved. It was the existence proof that launched an entire research field. Every quantum error correcting code developed in the early 3 decades since owes an intellectual debt to Shor's original insight. The Shor code achieves its protection through a beautifully layered strategy, beautifully layered strategy. I'm rephrasing myself, that you can think of as double defense system. The outer layer addresses phase flip errors and the inner layer addresses bit flip errors. Rather than trying to design a single mechanism that handles both types of errors simultaneously, Shor combined 2 simpler codes that each handles one type, nesting one inside the other. The outer encoding works by representing the logical 0 and logical 1 states as quantum superpositions spread across 3 groups of qubits. This spreading creates sensitivity to phase errors. If a phase error affects one of the three groups, the relationships between the groups will be visibly disturbed. The inner encoding then takes each of these three groups and applied a repetition strategy within each group, making bit flip errors within any group detectable by comparing the three qubits in that group against each other. The result is that a bit flip error anywhere gets caught by the inner code, and a phase error anywhere gets caught by the outer code. To check for error without disturbing the protected information, the system uses a set of 8 independent stabilizer checks. 6 of these checks look for a bit flip errors by comparing pairs of qubits within each group. The remaining 2 checks look for phase errors by examining the relationships between the three groups. If all 8 checks report the expected result, no error has occurred. If any of them reports an unexpected result, the pattern of unexpected answers uniquely identifies which qubit was affected and what type of error occurred, permitting a precise correction to be applied. The Steen code, developed by Andrew Steen in 1996, represents a significant advance over the Shor code in terms of efficiency and elegance. Where Shor needed 9 physical qubits to protect one logical qubit, Steen found a way to do the same job with only 7. More importantly, Steen's approach introduced a systematic construction method, a recipe for building quantum error correcting codes from classical error correcting codes that already existed and were well understood. This connection to classical coding theory opened up a whole new avenue of research. The key mathematical insight behind the Steen code and the broader family it belongs to is that bit flip errors and phase flip errors, while physically different, can be addressed using the same kind of mathematical structure. The code is built so that its error detection scheme looks identical for both types of errors. The same mathematical pattern that catches bit flips is also responsible for catching phase flips, just applied in a different direction in the mathematical description of the quantum state. This elegant symmetry between the two types of errors is a hallmark of what are called CSS codes, named after 3 researchers who developed the framework. The Steen code also has a practical advantage that goes beyond mere efficiency. It supports a set of logical operations that can be performed in particularly safe way, where each physical qubit in one block is operated on independently with its counterpart in another block. This property, called transversality, is crucial for building actual fault-tolerant quantum computers, and we'll discuss it in detail later. The Steen code was thus not just a minor optimization of Shor's work, it was a step forward, a genuinely practical architecture. So let's look into Steen code, stabilizers, and logical operators. The Steen code's error detection relies on 6 independent checks, 3 of one type and 3 of other. The first 3 checks are sensitive to bit flip errors, and they are designed so that each check asks about a different overlapping subset of the 7 qubits. If a bit flip error occurs on any one of the 7 qubits, a unique pattern of which checks succeed and which fail will pinpoint exactly which qubit was affected. The remaining 3 checks do the same job for phase flip errors using the same mathematical structure but applied in the phase direction. What is beautiful about this arrangement is that the 2 sets of checks are completely independent of each other. A bit flip error affects only the first set of checks, and a phase flip error affects only the second set. This means the error identification process for the 2 types of errors never interferes with each other. You can diagnose the correct bit flip and phase flip errors simultaneously in parallel without any confusion about which type of error you are dealing with. The syndrome bits from the first three checks tell you everything about bit flips, and the syndrome bits from the last three checks tell you everything about the phase flips. The logical operation on this code, the way you perform computation on a protected information, are also elegantly simple. The logical bit flip operation involves applying a physical operation to all 7 qubits simultaneously, and one logical phase operation similarly acts on all 7. The fact that these logical operations spread uniformly across all qubits is not a coincidence. It is a consequence of the mathematical structure of the code and is precisely what enables the transversal gate operations that make the Steen code so valuable for fault-tolerant computation. Surface codes, the leading candidate. Let me introduce you to this concept. Of all the quantum error correcting codes discovered so far, surface codes are the current front runner for practical implementation in real hardware. The reason for their dominance comes down to the combination of factors that make them uniquely well suited to the physical realities of building quantum computers. Understanding why surface codes are special requires appreciating both their theoretical properties and their engineering advantages. Surface codes are defined as a flat two-dimensional grid of qubits where neighboring qubits interact with each other to perform error checks. This local connectivity is enormously important from an engineering perspective. Every other major error correcting code requires qubits that are physically far apart to interact with each other, which is extremely difficult to arrange in real hardware. Surface codes only ever require each qubit to interact with its 4 immediate neighbors, like squares on a chessboard interacting only with the squares directly adjacent to them. This can be implemented directly in the kind of planar chip architecture that modern fabrication technology excels at building. The error detection in a surface code works by periodically performing a large number of small local checks across the entire grid. Each check involves just 4 neighboring qubits. 2 types of checks alternate in a checkboard pattern across the grid. When an error occurs on a qubit, it shows up as a disturbance in the 2 adjacent checks that involve that qubit. The location of the disturbance points directly to the location of the error, which, like how a broken tile in a floor pattern stands out against the surrounding intact tiles. This intuitive geometric picture of error propagation makes surface codes remarkably transparent and easy to reason about. When a qubit in a surface code suffers an error, the consequences ripple outward in a very specific and detectable way. A bit flip error on one qubit violates exactly 2 of the nearby phase type checks, creating a pair of warning signals in the check results. Similarly, a phase flip error violates exactly 2 of the nearby bit type checks. In both cases, errors always come in pairs of violations. A single isolated violation is not possible for a physical error, so any single violation would immediately flag a measurement error rather than a qubit error. The process of figuring out what error occurred from the pattern of check violations is called decoding, and it is performed by a classical computer running alongside the quantum hardware. The decoding algorithm looks at all the violation locations across the grid and asks, what about the simplest pattern Or what is the simplest pattern of errors that could have caused this particular distribution or in distribution in terms of disturbance or violations? This minimum weight matching problem has efficient classical algorithms that can solve it quickly enough to keep pace with quantum hardware. The classical decoding steps runs continuously in real time as the quantum computer operates. Comparing the major quantum error correcting codes or QEC codes side by side reveals clear patterns in how the field has progressed and what trade-offs different approaches make. The Shor's code, while historically groundbreaking, requires the most physical qubits of the three for a given level of protection and has the most stringent requirements on qubit connectivity. Qubits that are physically far apart must be able to interact directly. These connectivity demands are very difficult to satisfy. Let me rephrase. This connectivity demands are very difficult to satisfy with current hardware architectures, which is why the Shor code, despite its historical importance, is not considered a viable path to practical quantum computing. The Steen code improves on efficiency and introduced transversal gate operations, but it still requires long-range qubit interactions that pose enduring challenges. Its advantage over the Shor code lies on its CSS structure, which gives it cleaner theoretical framework and a richer set of operations that can be performed safely. For a quantum computer that happens to support the kind of connectivity the Steen code needs, it offers a very attractive combination of properties: fewer qubits needed and more powerful gate set than the Shor code. The three codes we have studied in detail are not the whole story. Researchers have developed a rich zoo of quantum error correcting codes, each with its own strengths and targeted at different hardware platforms and computational goals. Understanding the landscape of these code families helps clarify both how much progress the field has made and how much work remains. The color codes are visually appealing family of codes defined on lattice, where three colors of tiles meet at every vertex like a stained glass window. They share many of the useful properties of surface codes but have some additional advantages. In particular, they support a larger set of operations that can be performed in a transversal, fault-tolerant way. Bosonic codes take a completely different approach, encoding quantum information in the oscillating motion of the single physical system rather than across multiple discrete qubits. These codes are being actively pursued by teams working with superconducting circuits and many optical platforms. More recently, a class of codes called low-density parity check codes has attracted enormous excitement because of their potential or dramatically reduce the qubit overhead compared to surface codes. These codes borrow ideas from classical communication theory and can in principle encode many logical qubits using only a constant multiple of physical qubits rather than the quadratic overhead that surface codes require. The challenge is that they typically require long-range qubit interactions, so turning them from a theoretical promise into a practical reality requires hardware innovations that are still in progress. The Floquet codes, meanwhile, offer a clever approach where the stabilizers you measure actually change over time in a repeating cycle, providing protection through the dynamic of the measurement process itself rather than a static code structure. Having a good quantum error correcting code solves only part of the problem. Even if you can store quantum information in reliably information reliably in an encoded state, you still need to perform computations on it. And the gates, measurement, and operations that make up the computation are themselves source of errors. If the error correction process itself introduces errors that are spread through the code and corrupt the logical information, then no amount of clever encoding will save you. This is a challenge that fault tolerant quantum computation addresses. One of the most important tools for achieving fault tolerance in practice is the concept of transversal gates. When you perform a logical operation on encoded qubits, you need to apply physical operations to the underlying array of physical qubits. A transversal gate is one where each physical qubit in one logical block is operated on only together with its counterpart in another block, with no interactions mixing different positions within a block. This structure guarantees that an error on qubit number 3, say, can only affect qubit number 3 in the output. It cannot propagate to qubit number 7 or qubit number 12. For the CSS code, including the Steen code, a rich set of logical operations can be implemented transversally. These include the Hadamard gate, which creates superpositions, the controlled NOT gate or CNOT gate, which creates entanglement between two qubits, and several other fundamental operations. Together, these form what is known as the Clifford group of operations. For many purposes in quantum computing, Clifford operations are sufficient, and having them implementable in a traversal, fault-tolerant way is tremendously valuable. Clifford operations alone are not powerful enough to run every quantum algorithm. There is a theorem in quantum information theory called Easton-Nel theorem, or EKT, that proves no quantum error correcting code can have a transversal set of gates that is universal for all quantum computation. In other words, there is always at least one gate that cannot be implemented transversally. For most codes, the missing gate is the T gate, which is rotation by 1/8 of a full turn. The search for ways to implement this gate fault tolerantly without transversality led to one of the most important and costly constructions in all quantum computing, which we discuss next. Magic state distillation is the standard solution to the problem of implementing non-transversal gate fault tolerantly, and it is one of the most significant sources of resource overhead in any realistic blueprint for a fault-tolerant quantum computer. The core idea is to prepare a special type of quantum state called a magic state that encodes a missing gate, and then consume that state in a way that supplies the gate to your data qubit without the state preparation needing to be fault-tolerant in the traditional sense. The challenge is that preparing magic states is itself an error-prone process. The states you prepare directly from physical hardware will be noisy, imperfect versions of the ideal states you need. The distillation process is a clever protocol that takes many copies of noisy magic states as input that produces a smaller number of much higher fidelity magic states as output. The error correction in the output are dramatically smaller than the errors in the inputs specifically. The error shrinks much faster than the number of input copies consumed by running the distillation process multiple times, feeding the outputs of one round as inputs to the next. You can achieve arbitrarily high fidelity magic states. The catch is the resource cost. Producing a single high quality magic state requires a large factory of physical qubits running many rounds of distillation, and each logical gate that uses the T gate consumes one magic state. In current estimate, the scale of quantum computers needed to run useful algorithms The magic state of factories occupy the majority of the total qubit budget, often more than all the data qubits combined. Reducing the cost of magic state distillation is one of the most active and practically important areas of research in fault tolerant quantum computing today. The threshold theorem is the foundational theoretical result that identifies the entire enterprise of fault tolerant quantum computing. It answers a critical question: is there any error rate low enough that a quantum computer can actually compute reliably? Or does adding more qubits always make things worse by adding more sources of error? The answer the threshold theorem provides is profoundly encouraging. Yes, there is a specific error rate below which reliable computation becomes possible, and above which it does not. The theorem states that as long as the error rate at each physical component, each gate, each qubit, each measurement is below a certain threshold value, you can perform computations of arbitrary length and complexity reliably. The keyword is arbitrary. With enough physical qubits, you can push the effective logical error rate as low as you need, regardless of how long your computation is. Below the threshold, adding more layers of error correction makes things better. Above the threshold, adding more layers makes things worse, because the error correction process itself introduces more errors than it removes. The threshold value depends on the specific error correcting code and the specific error model you assume. The threshold theorem is a mathematical guarantee, but like all mathematical guarantees, it comes with assumptions that must hold in the real world for guarantee to be meaningful. The understanding these assumptions is crucial for interpreting what the theorem does and does not promise about actual physical quantum computers. Several of the assumptions are idealized in ways that current hardware only approximately satisfies. Knowing that fault-tolerant quantum computing is theoretically possible is one thing. Knowing how many physical qubits you actually need to build something useful is quite another. And the numbers are sobering. A single logical qubit, one well-protected qubit that quantum algorithm can use with confidence currently requires on the order of 1,000 physical qubits when implemented with a surface code at a level of protection sufficient for real computation. This is not temporary limitation of current hardware that will go away as technology improves. It reflects the fundamental overhead of the error correction process. Different physical platforms for building qubits each have their own strengths and weaknesses. With it comes to implementing quantum error correction and the choice of platform shapes, which codes are practical. Superconducting qubits, which are the technology used by Google and IBM, operate using tiny circuits that must be cooled to temperatures colder than outer space. They have very fast gate operations and can be fabricated using techniques similar to classical chip manufacturing, making them promising for scaling. Their main weakness is that they lose their quantum coherence relatively quickly, requiring fast error correction cycles. The history of the experimental quantum error correction is a story of steady, hard-won progress over about 2.5 decades. Early demonstrations in the early 2000s used nuclear magnetic resonance systems, the same technology behind medical MRI scanners, to show that the basic principles of quantum error correction worked in a controlled setting. These early experiments were proof of concept rather than practical demonstrations, but they confirmed that theoretical ideas could be physically realized. This module has taken you through one of the most intellectually rich and practically important areas of modern science and engineering. We began the most fundamental observation: quantum computers are extraordinarily fragile and the kind of errors they make are far more complex and varied than anything classical computing has to deal with. Decoherence, gate imperfections, and measurement errors conspire to destroy quantum information on time scales that are far too short for useful computation unless something is done to protect against them. We then explore the remarkable fact that two seemingly insurmountable theoretical obstacles and no crowning theorem and the continuous nature of quantum errors can actually be worked around through clever use of entanglement and discretization of errors during the syndrome measurement. The Shor code showed for the first time that complete protection was possible. The Stein code showed how to do it more efficiently and with better properties for computation. And surface codes showed how to do it in a way that is compatible with the physical realities of building large scale hardware with the highest known error threshold and purely local qubit interactions. The threshold theorem ties everything together with a profound message: below a critical error rate, reliable quantum computation is not just theoretically possible but practically achievable with enough physical resources. We are living through the moment in history when experimentation hardware, in reality experimental hardware, where the experimentation is happening, is crossing that threshold, and the enduring challenges has shifted from can we build error corrected qubits to how do we scale to the millions of qubits needed for transformative applications. Quantum error corrections is the field that makes a difference between a quantum computer that is scientific curiosity and one that changes the world. So no qubit left behind, in reality, is the mantra. Happy learning. See you in the next lecture.